Okay, good afternoon, everyone, and welcome to our favorite seminar. So we had a bit of a break over Easter and just before that, so it's good to have you all back. As you can see in my background, spring has arrived, so I made a little picture of my apple tree, so to demonstrate that. Yes, so today we have a double act again, so very good. Two speakers, one from Darmstadt and one from Marburg. So Lars is in Darmstadt, working on triple graph grammars there and applications and implementations of them. I think mostly what he'll tell us about that in a moment. And Jens is a bit more on the theoretical side. So between them, they have it all covered very well. I'm sure, and the talk is entitled "Recent Developments in TGG-based synchronization," which suggests that there have been lots of earlier development, to which I assume we'll get a little bit of a background at least. But just for everyone who hasn't heard about triple graph grammars before, so they are a development deriving from graph transformation, specifically for the specification and implementation of model transformations. I can't remember exactly, but I think it must be nearly 30 years old now, if not more. I think Andy was there earlier, so he may be able to tell us. I remember a paper saying with the title of sort of 20 years of triple graph grammars, but I can't remember when that was. But so there is a bit of history to these things. They are used, as I said, in model transformations. They have developed their own branch of theory specific to address these problems in model transformations. And yeah, so apparently haven't still run out of problems to solve yet. So looking forward to see what happened there in the recent developments. So I believe Lars is starting. So please, Lars.
Okay, yeah, well, thank you for a kind introduction. So let me also welcome you to today's GReTA seminar. And together with my colleague Jens Kosiol, we will talk today about our last results concerning model synchronization based on triple graph grammars. And maybe again, a little heads up, our talk, as said before, is split into two sections. And in the first part, I will informally introduce and motivate TGGs. Also, I try that to do for a, let's say, broader audience. As I heard, it's the talk is archived for future generations. And then I will talk about concurrent model synchronization, in which two correlated models can change independently, and for which we must then find conflicts. And in the second part, which will be presented by Jens, there he will, on a more formal basis, discuss a way to automatically derive repair rules from a TGG specification that lets us preserve a lot of information during change propagations. Okay, that being said, let's directly dive in. So what is the general motivation behind model synchronization? Well, take software systems, for example. There we encounter a lot of different people, like system architects and requirements engineers to design the software and collect requirements during planning phases. Then we have developers and testers who implement the actual software. And of course, the customers themselves who order the software must also be integrated into the process to make sure that the project stays on track. And someone, of course, has to maintain the software during and after its deployment. So here we encounter a lot of so-called stakeholders that have to communicate somehow. So, and if we take the upper four of them, we see that all of them, they have their own artifacts on which they work on, like the requirements engineer might think in use case and user stories, while the system architect maybe designs class diagrams, the developer writes code, and testers might work with the code documentation. And all of these artifacts can be perceived as graph-like structures, which we refer them to as models. And now in the initial phase of our software project, makes sense to have a first draft of our design, for example, as a class diagram, before implementing anything. So in that case, it might make sense to generate the first version of our program code with meaningful steps from this class diagram. And during development of the actual code, it is also important to synchronize changes backwards so that, which would have an effect on the class diagram, without having to explain to the system architect every change in detail, right? So this means that we should be able to synchronize information bidirectionally. Okay, and generally we can divide the task of synchronizing models into sequential and concurrent model synchronization. And in the sequential case, a source model is changed and the changes must be propagated to our target model. And these changes can be new elements, which is depicted here in green, or the deleted elements depicted in red. And one of the major goals when synchronizing here is to avoid unnecessary deletions during propagation. Like the trivial solution that you can think of is removing all the elements in the target model, just throwing it away and retranslate the source model from scratch. As you can probably imagine, this is usually quite a bad idea because unnecessarily removing elements means to first possibly lose information that might not be recoverable, and retranslating larger parts of my source model might also be quite expensive. So we thus aim for a solution that should scale with the size or the complexity of changes and not with the size of the models on which the changes are applied. And our approach to solve this is to derive repair rules, so-called shortcut rules, completely automatic, which are derived from this consistency specification here. These are our graph from us. And these rules can then propagate changes much more efficiently than before. And the second case is that of concurrent synchronization, in which both models can change independently from each other. And as commonly known from, for example, code version control systems, such changes might be in conflict as they contradict each other. So what we came up with is a new approach to detect these kinds of conflicts by analyzing a dependency graph that is based on our consistency specification. And having identified the conflicts, we then offer various components that can be used to implement specific synchronization goals and orchestrate the whole synchronization process in a very modular way. And in the first part of this talk, however, we will focus on the concurrent synchronization, while the second part will focus more on the sequential case. So as mentioned on the last slide, concurrent model synchronization shares some similarities with code version control. So in this example, we have a document with code that has version 1.0. And for a new feature, we create a new branch in which this document is then, for example, developed further. And at the same time, more branches could exist in which the same document is extended by other features. And at some point in time, of course, both branches must be merged onto the main branch again, in which case their code lines must be compared to detect conflicts between changes of both branches. And these conflicts are then usually resolved by a user by hand. So far, so common, right? But in case of model synchronization, this task is in fact much harder, because when synchronizing models, we do not only have different versions of one and the same document, but we may encounter different formats and structures on both sides. And to make it even harder, a model could contain information that is not present in the other one. So this means that we encounter an asymmetry that we have to take into account. And let me demonstrate this on an example. On the left side, we see a meta model depicted as a class diagram that shows a very rudimentary structure of implementation models. And it consists of classes that have names and subclasses. A class can have multiple methods and fields, and the method can contain parameters. And on the opposite side, there is a simple documentation meta model consisting of docs that are interlinked by hyperlinks, and where each doc should in the end correspond to a class. Besides that, a doc reference entries that should represent fields and methods on the other side. And both docs and entries have a name, as we can see, and docs above that also contain information about their version, which is information which is not present on the source side. So if we want to keep models now of both sides somehow synchronized, we currently face a problem of not having the means to tell which elements on one side correspond to another on the opposite side, right? So using triple graph commas, we solve this by introducing a third meta model in the middle, which is commonly referred to as a correspondence meta model that relates both sides. So the newly appeared hexagon-shaped correspondence node here connects now class with doc instances. And further correspondence nodes then connect methods and fields with entries. And since there is no representation for parameters on the target side, we might just connect these to the entries of their respective methods. And having defined the structure of these model triples, we can then express a consistency relation between implementation and documentation models using a set of triple graph grammar rules or TGG rules. And in general, TGGs are a rule-based and declarative approach to describe how consistent models are created simultaneously. So basically, this means that a TGG describes the language of all consistent model pairs. And our first rule C, that is shown here on the top left, thus describes that the creation of a new class, which is depicted here in green and with a double plus, always also means to create a corresponding doc on the opposite side and a correspondence link in between them. And also both elements must share the same name as stated by the attribute condition on top. And this rule can now be applied arbitrarily to create new class doc pairs. Okay. The same does not hold for our second rule SC, which appeared here, which allows us to create subclasses and corresponding subdocs, but only if another class doc pair already exists. And this precondition is here depicted in black. And analogously, we can use a rule F to create fields with corresponding entries that share the same name, which also holds for the rule M that creates methods. And finally, since our parameters have no representation on the target side, we connect them simply with the entry that corresponds to their method using the rule P. And here you can see how the asymmetry that I talked about, so between both structures of both models, can be incorporated into the design of our models. And using this rule set now, we can create consistent models basically from scratch. So we apply the rule C and create a collection class and doc. Then we create a subclass and doc using the rule SC, followed by a new field and entry with rule F, a new method with entry with rule M, and then two parameters, each with rule P. And we know that the result is consistent with respect to our TGG. And on top of that, the TGG gives me another thing, which is called a precedence graph of rule applications. And this graph basically depicts the dependencies between all rule applications and which applications depend on the prior applications of others. So, and each precedence node here consists of its root's name and two squares that depict the state of the source and target side. And currently we can see that these boxes are just blank, which means that they are still intact, but in the following, this will change and we will be able to determine the current state of consistency of our models just by looking at these precedence graphs. Okay, that being said, of course, it is usually not that exciting to create consistent models from scratch, because normally we already have one model and we want to get the opposite one, or we want to propagate changes between formally consistent models. So for that purpose, we can operationalize our rules to yield, for example, forward rules that translate implementation to documentation elements, or analogously obtain backward rules. We can also derive consistency check rules that can be applied if we want to get a mapping between two already existing models. And finally, we can also derive consistency patterns that do not create any new elements that give us the location of consistent TGG rule applications, which lets us then deduce consistency violations if such a location suddenly vanishes. So, and now how does the application of these rules look like, at least let's say roughly in practice? Well, I have this rule set, and of course I have my models. And these are being observed by an incremental graph pattern matcher, which reacts efficiently to changes of our models. And the pattern matcher then sends notification to a TGG engine about newly available rule applications or recently vanished ones, or even also consistency violations. And this TGG engine is in our case the open source graph transformation tool Imoflon. And Imoflon then step by step applies a rule and thereby changes our models to the point where they are hopefully again consistent at some point in time. Okay, so before we can see an actual synchronization scenario, it makes sense to first talk about how to obtain forward rules. As we can see here, the green class element C on the source side turns black if I want to get a forward rule, because this element now becomes part of the rule's precondition, as it must exist beforehand. So instead of creating another element on the source side, we would rather translate this element and create the missing elements on the target side. And to make sure that the element C is not translated twice, we have to mark it as translated, which is indicated here with these little boxes and the marking sign. And we can do the same for the SC rule, where again, the formerly green elements on the source side turn black. However, the class C1 already was part of the rule's precondition. So instead of marking it again, we state that in order for this forward rule to be applicable, it must have been translated by another rule before, which I hope makes sense. Okay. So, okay, the rest of the rules can be operationalized in the same manner. And using these, we can now look at a concrete, although still sequential synchronization example. And on this slide, we can see two changes. The first being that the class collections on the top, in the top left, has been deleted together with the adjacent edges. And this change is also represented in our precedence graph on the right as an entire deletion of all created source elements, which is annotated here with a minus, in the precedence node C, which is here on top. And the node underneath has also lost elements, namely the subclasses edge. However, its list class still exists, so it has not been touched, which means that this was only a partial deletion that we here annotate using a slash. And since the list class is now a root class itself, a new precedence node has appeared on the right, which indicates the possibility of retranslating the list class with our rule C. Yet this star symbol tells us that the list class is still part of some other rule, which we have to clean up first before we can just retranslate the class. And as a second change, we added a new parameter on the source side, which could be translated using our parameter rule P. The corresponding precedence node on the right depicts us with a plus for the parameter and an undefined for the target side. And, and this undefined basically means that we are not sure whether there are already elements on the target side that would correspond to the source side change. So although this might not be interesting for the sequential case, we have to account for that when we perform concurrent changes or concurrent synchronization tasks, where independent changes on both models might already correspond to one another, and then I may want to map them onto each other. So now if we want to synchronize these changes, we must first deal with the ones that violated formerly intact rule applications. And since all source elements of the C rule application on top were removed, we consequently must also get rid of the target elements as well, which is here our doc element on top. So doing so, we can now see that there has been another partial deletion, this time on the target side of the SC node. Since the SC node's consistency is still violated, we must retranslate the source elements, which means to revoke target elements first. And yet deleting the list doc also violated the rule application M because the remaining entry is no longer contained in the doc. So we also have to delete it, and now we reach a point where no source elements are marked any longer and we can restart the translation. So in the first step, we will translate the list class to a new doc. Then we translate the add method by creating a new corresponding entry. And then we translate both parameters each. And at this point, both models are again consistent, but there are 2 points I want to highlight for you. First, we have lost information in the process, namely the version of the list document, which was 1.0, and now it is just 0. So since the information about the version is only present on the target side, we have lost it when we deleted the old list doc, and we cannot reconstruct it from the source side only. And second, we have in fact performed quite a lot of deletions and retranslations to obtain a structure that actually closely resembles the one that we started with. So we might ask ourselves if there's not a more clever way of performing these propagations that repair the model like the list class, instead of simply revoking all these rule application steps. And this is something that Jens will talk about in more depth in the second part, where he will talk about shortcut rules. And although this is a worst case scenario on how to synchronize changes, it shows us how usually changes were propagated using TGG rules. Okay, then finally, let us talk about the case of concurrent synchronization. Let's start with the state of the art, which can be divided into 2 methodologies. So first, we can do this propagation-based, where we perform sequential synchronization steps like first a forward and then a backward transformation, or vice versa. And in case that the propagation step overrides a user change, we have detected a conflict between these operations. And the advantage of this method is that it is theoretically very fast and easy to implement if we already have a sequential synchronizer, like the one I sketched on the last slide. The problem of using this method, however, is that the detection of conflicts might depend on the order of the actual synchronization steps, which means that conflicts are not detected reliably and user changes might get overridden without us even noticing it. And this happens, in fact, due to the aforementioned asymmetry of our models. And on the other side, there are constraint-based methods that model the search space of, let's say, most of all synchronization solutions, like in the form of some sort of supermodel, and then they employ techniques like ILP solving to get an optimal solution with respect to some objective function. And our experience with these methods was that they can often be extended quite elegantly, and that they do not need the notion of conflict as they solve these implicitly. And in practice, this is, however, quite problematic, or it can be, as a user is thus never asked on how he wants to actually resolve a conflict. And in fact, these approaches are also mostly very hard to configure because someone has to define a metric that encodes all possible situations and conflict resolutions before, which is then given to the solver. And above that, by using optimization techniques, they are also only applicable to models of rather small size only. And as an alternative, we proposed a precedence-driven synchronization approach. The criteria on what this approach should offer were that it shall work incrementally and delta-based, which means that we only react to changes of our models. And we therefore hope that the runtime was also bound to the complexity of a change rather than the complexity of the overall model. And besides that, we want to detect conflicts efficiently and reliably, and above that also non-invasively, which basically means without even touching the models themselves and changing them. We rather wanted to detect conflicts by keenly investigating them. And our solution to this is based on the annotated precedence graph that I showed before, and which can be used to deduce conflicting situations, which can then be resolved using predefined strategies of us. And after having resolved all these conflicts, we then rely on propagation-based synchronization to propagate all uncontroversial changes efficiently that are left. And the benefit of doing this is that we can orchestrate the whole process and use a lot of formally developed components of the past in order for modelers to implement their individual synchronization orchestrations. Okay, that being said, how can we detect conflicts using our precedence graph? Well, to show that, we have added a new parameter here on the source side, while we deleted an entry on the target side that corresponds to the parameter of method. And what we see here is what we call a delete preserve conflict. Now let's check why this is an actual conflict. Because if we want to translate the parameter from the left to the right, we would have to connect it with the entry that corresponds to its method. However, this entry was deleted, so we cannot do that at the moment. The precondition is currently violated. If we do it the other way around, starting from target side, I could try to propagate deletion of the entry instead. So if I do that, we can see that our newly added parameter is now detached because we deleted the newly created parameter's edge implicitly together with the method. And obviously, this must mean that both changes conflict, which we can also see in our precedence graph on the right. Because there, the minus in our node M tells us that we have to react to this change with a deletion of its created source elements. But by doing so, the node M would vanish entirely, but then the new node P, which depends on M, would lose all elements that are needed to translate the parameter. And this means that we can detect this conflict by simply traversing over our precedence graph and searching for locations where a node with a plus on one side depends on another node that has a minus on the other. And another kind of conflict is depicted on this slide here. This time we have three classes, collection, list, and array list, with corresponding docs on the opposite side. And what we do now is that we will move the method and entry on the bottom, which will then cause a correspondence preservation conflict. So in the first step, we move the method from the array list class to the list class. And in our precedence graph, we can see this change as a partial deletion of our node M in the middle. And at the same time, we could now retranslate the method using the list class as a precondition. But first, we would need to revoke the former broken M root application in the middle. So now the second change looks very similar. Here we have moved the entry from the array list doc to the collection block on top. And the result is again a conflict, as both relocations do not match, because a method entry pair should always be contained within the same class doc pair, but this is clearly no longer the case. And we can see that on the left in our rule M. So we thus have to decide which relocation we want to preserve and which should be dropped, as long as we do not want to delete the correspondence link between both elements so that they are translated each anew and we get copies of them. And again, we can detect this kind of conflict easily in our precedence graph when finding a node such as the one in the middle, which has consistency violations on both the source and the target side. But it is noteworthy that both sides have not been entirely deleted, right? Which indicates that the modelers on both sides that applied these changes wanted to preserve at least some elements. And since both newly appeared precedence nodes do not depend on the same elements, we can conclude that both relocations do not match up. Okay, and finally, let us discuss a third conflict, which is the attribute conflict. In the beginning, we stated that the method and its entry should share the same name. So if I change the name of the method from clear to remove all, this condition is already violated, but we could easily fix this by just propagating the new name to the entry on the other side. Now, if another modeler decides to change the entry's name simultaneously and in such a way that it does not match the method's name, we again have a conflict. In case that we encounter attribute change annotations on both sides of one precedence node, which are also only detected if a related attribute condition is violated, then we also have detected this kind of conflict. And it is also noteworthy that this does not only hold for simple equality constraint, but also for more complex ones. Okay, so now that we can detect three kinds of conflicts, we still have to resolve them somehow. And while one can surely put a lot of energy in designing user-defined strategies, we provide four predefined ones. And we will demonstrate them on the delete preserve conflict on top, which is caused by adding a method on the left while deleting a doc and its entry on the right. And the strategies that we can choose from are take the source changes or take the target changes, preserve new information, or delete the mapping, which can then individually be applied to each conflict. So if we take the source side changes, then we drop all target changes and do not delete any elements there. And this means, of course, that the conflict must be resolved, since we cannot translate, that we can now translate the new method, since all elements of the preconditions are not present. The same holds if we prioritize the target changes and drop the source side changes. In that case, we delete the doc and its entry, but we no longer add the method on the source side, which would conflict with the propagation of both deletions. And the third strategy is based on the idea of preserving new information, such as a newly added method, but without dropping all deletions on the opposite side. Because if we have a closer look at our example, we will see that the actual conflict here is between the creation of the method and deletion of the doc. And deleting the entry, however, does not directly conflict with the newly added method, which means that we could still decide to revoke the doc's deletion and keep deleting the entry. And as a final strategy, we can also decide to delete the correspondence nodes, which would mean that both models are no longer related and would have to be translated from anew, at least around this conflict. And in this case, we would translate the class and both methods from anew. Of course, this strategy might not be that useful for delete preserve conflicts, but for example, for correspondence preservation conflicts, where we might want to preserve two relocations by making copies of the affected elements. So, and in general, we need also, we have a lot of configuration options to achieve the desired result when synchronizing our models. On the last slides, we saw the conflict detection and the conflict resolution components, where beside the four strategies that I showed you, we could, of course, also decide to skip a conflict and resolve it later. Then we could decide whether to translate new elements, or if we want to try mapping them to other newly created elements on the other side, for which we can use a consistency check component. We can also decide to roll back broken rule applications, as we have seen before, or we try to repair them instead using shortcut rules, which might save information and often reduces the number of necessary propagation steps. And finally, we might want to get rid of all inconsistent parts of our models that still persist and for which there are no valid rule applications that explain them. And in summary, we can see that there are a lot of options that a modeler can use to control the synchronization process, and he can orchestrate these components in a specific order to achieve his goals. And the good news is that this approach was integrated into the graph transformation tool in Modelon, which is, as mentioned earlier, is based on incremental graph pattern matching. And the orchestration of these synchronization components can be done via a programmatic interface. And to show you some numbers on how the approach performs, we brought with us two research questions, with the first being whether the runtime actually depends on the size of the changes rather than the size of the model. And as a second question, we wanted to know whether it makes a difference for the detection of conflicts if not all changes lead to an actual conflict. And to answer these questions, let's investigate two scenarios. Here in the first, we applied 500 changes onto our models that each led to an actual conflict. And we increased the size of our model until we reached around 1.5 million elements on source and target side combined. And we measured first the initialization time in which rule applications are found. And then we measured the time it takes to detect and resolve conflict, so meaning the actual synchronization. And as a result, we can see an almost linear relation between the size of the model and the initialization time, which makes sense. The time it takes to analyze and resolve the conflict also increases slightly, doubles from 7 seconds to 14 seconds, while the model size increases by a factor of 9 at the same time. We would have expected here a constant number. The most probable explanation for this are, in fact, technical reasons such as map collisions due to the size of our models. And in the second scenario, we basically did the opposite thing and fixed the model size at around 1 million elements. And then we increased the number of changes to around 3,000 and again measured the time to detect and resolve conflicts. And besides that, we also measured whether it makes a difference when only 25, 50, or 75% of all changes actually inflict a conflict. And as we can see, apparently there is almost no difference when comparing the measurements of uncontroversial and controversial changes, which already answers our second question. And also we can see that the time scales linearly with an increasing number of changes here, which together with our last slide tells us that the runtime is primarily related to the complexity of changes instead of the model size, at least for this example. Okay, so before continuing with the second part of this talk, let me shortly summarize. I have shown you a precedence-driven concurrent synchronization approach that detects conflicts non-invasively and which does not depend on the order of propagation steps. And also we saw that the runtime is quite promising, although this has to be replicated with other scenarios. And then again, our approach is highly configurable and can be used to implement individualized synchronizers. And in the future, we will investigate networks of synchronizers, and we also want to tolerate inconsistent states, at least for some time. A possible way to do this would be to incorporate hard and soft constraints, where the hard constraints must not be violated under any circumstance, and soft constraints might be violated for some time and, yeah, to some degree. And yeah, that was the first informal part of this talk about TGG-based model synchronization. I'm sorry for rushing it a bit, but I hope you enjoyed it, and my colleague Jens will now continue with the second part. Thank you very much.
Yeah, can you see my slides?
Yep.
Okay, nice. Yeah, also hello from my side, and thanks for the nice introduction at the beginning, Reiko. The aim of my part of the talk is to provide some of the formal developments and the formal ideas behind what Lars just explained to us. But concerning the formal results, I will basically stick to the sequential case. So to the case where we are given two models, but only one of them has been changed. Okay, the starting observation for our formalization is basically, like Lars explained, TGGs are a monotonic grammar. Monotonic means every rule just creates structure. There's no deletion by the rules that define the grammar. And a lot of works on TGGs has argued about transformation sequences because consistency is defined by transformation sequences via rules of the given grammar. And if I want to know that the triple graph that I'm working with is consistent, it belongs to the grammar of the language, I need to know that there is a transformation sequence with the rules of the grammar which constructs this graph. But if we now have a closer look at such transformation sequences, we have a monotonic grammar. Every rule just creates structure. So if we have a transformation sequence that creates a graph from our grammar, we can see that this provides us with a family of morphisms from the right-hand side of the rules. So formally, a rule consists, a monotonic rule which only creates structure consists of two parts, a left-hand side, always L in this slide, a right-hand side R, and ejective morphism between them. So the difference between the two graphs is the structure that is created by the application of the rule. Application of the rule is basically a push out, only structure is added. And so the co-matches from the rule application, they
Sorry, Jens, we can't hear you anymore. Is that only on my end? Or everyone else?
I can't hear you either.
Okay. Somehow you switched off your audio, I think. They're not on mute, so it's certainly the... Oh, you stopped moving as well. The slides are still moving. We just need to wait for a moment. Yeah, I'm not sure. Do you have a phone number, Lars, maybe that you can call? Yeah? Maybe call him to see what goes wrong there.
I think he realized that we can't hear.
Yeah. Okay, I just let him in again. I have him twice now.
Can you hear me now?
Yeah, we can hear you.
I'm very sorry. Sometimes the computer at my university somehow stops Zoom meetings, so he basically freezes. Can you again make me a co-host, or I seem to?
Let me see, I'm sure I can.
Very sorry for that.
You are a co-host already, as far as I can see.
I think that's only the user on the other.
The other session is only co-host.
Yeah. Thank you.
Can you try now? Yeah, it should work
Yeah.
now.
Okay, yeah, I can see that.
Yeah. So again, I'm very sorry. And I was talking about how from a transformation sequence, we get a family of morphisms via the co-matches. I will just speak of the co-matches, even if it's formally co-match composed with this tracking morphism. So I will just speak of co-matches. So transformation sequence, we get a family of morphisms from the right-hand sides of the rules. And if we assume that the start graph of such a transformation sequence is empty, the family of morphisms will be jointly surjective. And we will, for simplicity, we will restrict to this case. And for the other direction, I call this a correspondence, back from family of morphisms to transformation sequence. I will talk about that in a minute. Why are we interested in such families of morphisms? What does this switch of perspective help us? Families of morphisms are very flexible. So if the underlying graph changes, may it be a change performed by a user, per hand, or rule application, or whatever, we can encode this as a span, a pair of injective morphisms. And this change always provides us directly with an update of the family of morphisms. This might render the morphisms partial, but we still obtain a family of now maybe partial morphisms. That seems to be much more flexible than talking about transformation sequences. Formally, if I have such a morphism phi, and now the underlying triple graph GT is changed, I can compute the partial morphism performing a pullback of the morphisms phi I along the deletion that has been performed. And this will give us these markings about which Lars talked the whole time. Because basically all that he talked about have been partial morphisms from right-hand sides of the rules of the given grammar to the triple graph we are given at the moment. And for the direction back, when does such let's first formally define markings. We are given a triple graph and potentially partial means that formally, if a user is allowed to freely edit his models, which we formalize as a triple graph, he might delete a source element which is referenced by a correspondence element. Formally, that's not a triple graph any longer, because a triple graph needs to map each correspondence element to a source and to a target element, and so allowing free edits by users, the triple graphs we are working with potentially become partial correspondence morphisms. And we are given such a partial triple graph and a TGG. And now a partial marking is just morphisms from a partial morphism from a right-hand side of one of the rules to the partial triple graph that we are given. Quasi-injective means that this has to be injective except for attribute values. So formally, the graphs we are working with are attributed, and of course, an attribute value can, or for example, attribute values might be mapped to the same attribute value in G, so the morphisms have not to be injective on that. But marking just partial morphism from the right-hand side of rule. And then we can talk about required elements. The required elements of a marking are the elements which already stem from the left-hand side of the rule. So the intuition is, if I want to consider such a marking as co-match of a rule application, these are the elements which need to exist before I can apply the rule. If they do not exist, this cannot be, or if they not already exist in the situation where I want to apply the rule, I cannot apply the rule. And marked elements are of a marking are the image of the created elements. So if I want to consider my marking as co-match of rule applications, these are exactly the elements that the rule would have created. And finally, we define partial covers and images. Partial cover is just a finite family of such partial markings. And the image of a partial cover is the subpartial triple graph that is covered by the individual markings. So the common image of all the partial markings of the family. And now the other direction, how do families of such partial markings correspond to transformation sequences? Of course, not arbitrary families are families of co-matches of transformation sequences. We need some consistency conditions. And if we're given such a partial cover, we firstly introduce a dependency relation between the covers. So basically, one marking depends on another one. If the first marks an element which the second one requires, in terms of rule application, this would mean the first rule creates an element that the second rule then uses and matches for its application. And this is the direct dependence, and the dependency relationship we are considering is then just the transitive closure. What do we need? What consistency conditions do we need? First, we introduce the notion of marking consistency. This means the dependency relation is acyclic. And this is rather intuitive. If this should capture the dependency between rule applications, I cannot use elements that use the rule that need the rule that I just want to apply to be created in the first place. Coherence. So if I want to consider a family of morphisms as a family of co-matches that stem from a transformation sequence, every element is exactly created once. So no two of the markings can mark the same element. And then internal completeness or completeness. This just means that every structural element, this means graph nodes and edges, we do not need to mark the attribute values. So every structural element is also marked by one of the markings. And internal completeness means that this holds for the image. So I mark a part of the partial triple graph over which my partial cover is defined, and complete means if actually the whole graph is marked. Every structural element of the given graph is marked. And if a partial precedence graph then is a consistent, coherent, and internally complete partial cover. So a family of markings that satisfies all these consistency conditions. And the markings have to be total, because if they should constitute co-matches, obviously they need to be total morphisms and not partial ones. And then with these consistency conditions, we get our other direction. We can now say which families of morphisms actually constitute co-matches of transformation sequences. So we have this correspondence result, which states that if we are given a potentially partial triple graph G, and then the sub-triple graphs U of G, which stem from the language of the given TGG, they correspond to partial precedence graphs over G, which U as their image. And so in this case, for every sub-triple graph that actually stems from the language, I get a partial precedence graph, and from partial precedence graphs, from the images of partial precedence graphs, I get transformation sequences. And the correspondence is unique in a certain sense, namely up to switch equivalence. Whenever I construct a precedence graph from a transformation sequence and then reconstruct the transformation sequence from the partial precedence graph, I might have reordered the steps of the transformation sequence, but only steps which do not depend on each other. So, and topological sortings of such, this basically means that there's a one-to-one correspondence between topological sortings of the precedence graph with respect to the given dependency structure, and transformation sequences which are switch equivalent to the given transformation sequence. And the proof of this result is basically each directions can be proved via induction on length of the transformation sequence or number of markings in the partial precedence graph. Or otherwise, one could alternatively work out the connection of partial precedence graphs to so-called sub-object transformation systems, and for them an analogous result is already known. Okay, sequential model synchronization formally. Lars basically already introduced this. I just have a little more formal presentation of it here, we are given a TGG, we are given a triple graph that stems from the language, and we also assume that we know a precedence graph for this given triple graph from the language, and then a user edits the source graph. So he changes the source graph GS to another graph HS. And then the task is to compute another triple graph H, which has the same graph as source graph, so HS as source graph, but recomputes the correspondence and the target structure in such a way that we get into the language. So H should be a triple graph from the given language. And the side conditions are that we want to avoid unnecessary changes to the target and also the correspondence structure, and the whole procedure should be efficient. And the general approach that we follow is that we know precedence graphs correspond to triple graphs from the given language. Whenever a user changes a triple graph, this user edit provides us with a possibly partial triple graph. And as shown at the very beginning, each change always induces an update of this family of morphisms. Now it's normally not a precedence graph anymore, but merely a partial cover. But the partial cover contains information that we can use to extract knowledge about which synchronization operation to apply and at which place. And so we use information of the partial covers to decide how to synchronize. Every synchronization step again induces updates on the partial covers. So this family of morphism changes. And as soon as we recognize that the partial cover, this family of morphisms actually satisfies all consistency conditions, we know that it is a precedence graph, and therefore the underlying graph now needs to be a triple graph from the currently given language because of the correspondence result that I just mentioned. What kind of information is available from the partial covers? It's basically the not yet marked elements. They still need to be translated, and invalid markings that cannot constitute a co-match of a transformation any longer, and they somehow need to be replaced. And invalidity either means that a morphism is not total, then it cannot constitute a co-match, or, and I will not much talk about it, that such a marking does not satisfy its so-called filter NUC. That is a construction which allows us to determine that this marking cannot be part of a parsing process of the whole triple graph. So that's another case where we know that we need to get rid of a marking. Now I will shortly provide an example for how we construct our repair rules. The grammar is very similar to the one which Lars just used. So we have packages that correspond to folders. Packages may contain sub-packages, folders, subfolders. A subfolder has a corresponding doc file as documentation, and then packages and folders can contain classes and corresponding doc files. There's one example situation with a precedence graph which says how this graph can be created using the rules of the grammar. And the edges in the precedence graph are just the dependency relation. And in this situation now, there have been performed a series of changes on the source side. And the one that I want to concentrate on is this package SSP, the third package, which belonged to a package SP, but the package SP has been removed. And the package SSP has been moved to the package RP, which already existed. And now, how do we perform such a change? These are the kind of most interesting, most complex changes. And our main idea here was that basically removing retranslate or integrating this package in the correct way into the target part now basically is some kind of sequential rule composition. This package had been created by applying the rule create sub matched at RP once and then a second time. And now I need to reverse this process. So basically, I need to apply the inverse rules of these two rules at the induced matches to revert that process. And then I need to recreate this package with another application of create sub, but now matched differently, now matched at the root package. But of course, this would be highly inefficient because the package is still there. It might contain private information. I do not want to get rid of it. So we need a sequential rule application where I do revert some things and perform the same things again, but in a slightly different way. And to formalize this, we came up with this notion of our repair rules, a sequential rule application where where elements are allowed to be preserved. That's a kind of generalized concurrent rule construction. So concurrent rules is the normal construction for sequential rule composition. We are doing the same thing basically, but allow preserving additional elements in the process. So in this example, the concurrent rule would not reuse this spot in the derived rule, would not reuse the package and the folder at the very bottom, but would delete them and recreate them. And we formalize this rule construction where the elements are allowed to be preserved. And so for time reasons, I will not go into further details. I hope that this idea, I need to revert something, but I do not want to actually delete the elements, but I want to partially revert the process. For example, deleting this folder, but I do not want to revert the whole process, but only parts. And this is a kind of special sequential or a very general sequential rule composition. I hope that this intuition is enough. We formalized this generalized concurrent rule construction in the setting of additive categories for arbitrary linear rules. They are allowed to have application conditions and show that it indeed generalizes the well-known concurrent rule construction and that a kind of generalized concurrency theorem holds. And all of this is published at ICGT 21, last year's edition. And for our purposes, we then need one more further small adaptation. We assume that the change on the source side has already been performed by the user. So the package that the generalized concurrent rule would delete is already deleted by the user. And so we ignore these package, we ignore these changes on the source side, and our repair rule just performs the changes on the correspondence and the target side. Okay, we are a bit over time, so I will shortly mention how we use this in our repair process and then summarize our most important results. So how do we apply the repair rules? Now, this rule Collapse hierarchy forward, which we derived as repair rule, exactly performs the action that we would like to perform. It deletes the folder, which is unnecessary now, and just relocates the folder SSF on the target side in the right place. And or in terms of our partial covers, the first input for Collapse hierarchy was the reverse application of two applications of create sub, and there are two invalid applications of create sub in our partial cover, and we revert these. And the second input of our rule Collapse hierarchy forward was another application, a new application of create sub at a suitable match. So in terms of the partial cover, we remove these two markings which we just reverted by our repair rule and insert a new marking, create sub, at the right place. And so remember that these nodes in the partial cover, they actually correspond to morphisms, so they provide us with a partial match for our repair rules. And then I will directly switch to our central results. So we can prove termination for our synchronization process in case of source progressive TGGs, which means that every rule at least creates one element on the source side, and either we receive either an output or an exception, but we cannot get into a loop of indeterminate length and cannot notice it. We can prove correctness. So whenever we receive an output by our synchronization process, it's a valid triple graph with the right source graph. And under the assumption of source progressiveness and marking completeness, our synchronization process is also complete, which means we are able to compute a result for every input. And marking completeness, it's a technical precondition, and it is kind of restrictive, but it is less restrictive than the requirement of TGGs being deterministic, which has been used for other formal results in the literature. So we do not lose generality by this assumption compared to other works, and it's equivalent to a condition which has been used by Erhan Leblebici in his dissertation, on which our synchronization process is based. We basically take the synchronization process of and add the use of repair rules. And the common idea is arguing about the partial covers, arguing that in the end we will obtain a precedence graph again, and then using the correspondence result that precedence graphs correspond to graphs of the given TGG. And for every kind of synchronization operation that we employ, we define so-called legal matches, and using these matches we can argue that we push down the invalid marking, or we push the invalid markings further down in the partial cover. So it cannot happen that we try to repair something and then cause some new invalidity in a place we have already repaired, but this will get pushed down the precedence graph so that we indeed terminate. Yeah, further results is we can show that the runtime linearly depends on the size of the given input graphs in terms of calls of the incremental pattern matcher, which is the most expensive operation. And under favorable circumstances, the runtime even depends only on the size of the change. And we can prove that when repair rules are applied in our approach, it might happen that no suitable repair rule is available, and then our approach basically is exactly the same as the one of Erhan, but when repair rules are applied, the number of preserved elements, of preserved target elements and correspondence element provably increases. Yeah, thanks for your attention. And again, I'm sorry for the technical problems and the delay this caused.
Okay.
Yeah.
Thank you very much.
One further remark, which Andy reminded me of, this whole research was funded by the German Research Foundation, and the grant just got continued. So there will be successors for Lars and me who can continue the work, and especially the future work which Lars mentioned, considering additional constraints and dividing them into constraints that have to be satisfied and constraints for which it would be desirable if they are satisfied, but we are allowing for inconsistency regarding these constraints. So this is really future work that with very high probability will also be done.
Okay, excellent. Yeah, so thank you very much, Jens, and also to Lars for the nice presentation. So I don't know if you have a question here in the chat, and I can't see everyone at the same time, so I probably can't see if anyone has raised their hand just yet. But maybe I just start and then we see. So I have a kind of general question, and I mean, specifically, Jens, because you're working with Gabi, so you probably know about this. There is this formalism of distributed graph transformation. Yeah, so I don't know whether you've come across this, which basically means that you're rewriting arbitrary diagrams of over graphs. Okay, and one could think of triple graph grammars as a special case of that. In the sense that the diagram there has a particular shape, okay, and namely the three grammars that are related by the two morphisms, and then typically the shape doesn't change, whereas in distributed graph transformation, of course, the shape can also change. But from some point of view, at least as far as the basic definition is concerned, one could think of this as a special case. So this occurred to me. I mean, by itself is not a particularly deep statement, because the motivation is different and the theory is quite different. But also in distributed graph transformation, they considered two different variants essentially, or they considered essentially a variant based on partial morphisms in addition to the sort of traditional one that had total morphisms only, namely the idea that the basically two local states that are related by morphisms can be out of sync, essentially because you basically allow these partial relations, which mean that, for example, you create a node in one local view and then it should be visible in the other open view, but the other view isn't updated yet, so you get a partial relationship. It's basically like a distributed system that isn't perfectly synchronized. Where you have a delay like an asynchronous communication delay. So I was wondering, and so sorry. What I'm saying is they basically did this just by switching essentially the notion of distributed graph transformation from the category of total graph morphisms to the category of partial graph morphisms. Yeah, and essentially replacing double push out by single push out. And I was wondering whether a similar trick happens here as well. I mean, obviously, the way you formalize this is different because you represented the partiality explicitly by spans. Yeah, but I was wondering whether there's a similar idea behind this, and whether maybe a similar general solution could also be suitable. Triple graph numbers in partial morphisms, essentially.
We do this on the basis of our objects inside the objects with which we're working, but not in the definition of the rewriting steps. So we do not consider partial morphisms as matches for our rules, or partial morphisms as our rules.
Yeah, but single push out would also work with total matches.
Yeah.
As you know, I just see an analogy there. I don't know whether there's a technical relationship, but it seems to be a similar kind of problem, in the sense that you want to have a framework that is more liberal, in the sense that allows inconsistent or sort of basically allows states that are kind of out of sync. In as I said, in that case, the solution was to basically replace the total morphisms by partial ones, but not all of them. I mean, basically the ones that are between the morphisms between the local graphs, essentially.
Yeah. So basically we are doing this as well. Instead of working in the normal category of triple graphs, so the functor category over a span of graphs, we switch to a category which basically is also a functor category over two spans, which with a central node, and we require that the morphisms to the central node are injective to be able to express this partiality. And the formalization of this is presented in this double push-out rewriting in as Cartesian functor categories, the number 5 on the list. So we just switch the category in which we work, and then are using basically it's double push-out and sesqui push-out rewriting in that category, because our repair rules, or and also the revocation of rules, because we want to work top down to get termination, and then we need to be able to already delete dangling edges working top down, and therefore sesqui push-out rewriting. But I cursory read about this distributed graph transformation, and I know that they are able to switch the base structure. And I remember that I thought that this would, if I would fix the base structure, then it would be rather similar. But I didn't see how they were able to to fix these morphisms that we needed to be injective to also be injective. But it could be true that I missed something.
No, I don't. Yeah, I see what you mean. Yeah. I don't think in that DPO total framework you would get that very easily. As I said, if you take a category if you take a diagram, if you take a distributed graph as a diagram in the category of partial graph morphisms, then of course the notion of partial morphism is already built in there. Yeah, and that would imply obviously that the domain is embedded into the source object basically by a mono. If you look at this as a span. Okay, but that's fine. I just wanted to understand this kind of, it was just a thought that occurred to me. So right, so I think Paolo had a question about the relationship of the precedence graphs with layered graph grammars. So layered graph grammars, I don't know if you're aware of them, are basically a mechanism to some extent control graph grammars, but also to prove termination. And your precedence graphs have some kind of similar. They also define an ordering basically on the elements of the graph. I think in that sense there's some similarity there. But have you looked at layered graph grammars? Have you seen those before?
Not really. Okay, Jens, you?
I'm aware of this work where layered grammars are used for model transformation. So that you sort your rules into layers, and then it's easier if the layers interact nicely. You have this nice modularity to prove termination and deterministic behavior, because you only need to consider the rules inside each layer individually. And I'm aware of that. And I don't see an immediate connection between the precedence graphs and layered graph grammars, because, I mean, obviously it depends on the given TGG where a rule can, or where a co-match of a rule can occur in such a precedence graph, but theoretically any rule of the grammar can occur anywhere. It's there is a close basically a precedence graph is a parsing tree.
Yeah,
and
I don't know.
We
I mean,
relax this.
Paolo, maybe Paolo can sort of elaborate on what he wanted to suggest there.
Or Lars, do you? Can
Paolo
you
is on YouTube, so he cannot directly.
Oh, yeah, on YouTube. Okay.
So we will have to wait for 1 or 2 minutes.
Yeah.
The delay. Yeah.
Okay, so my instinct maybe is that, I mean, I think one thing you said is, I think it makes sense. So the parse tree is obviously it's a structure that you get by analyzing the grammar. So you're not restricting the grammar in the first place, but you're analyzing the derivation that is produced by the grammar. So the precedence graph is essentially the result of the analysis of the transformation sequence, and not an input that restricts the transformation as the layering would be. So that's clearly a difference there, isn't it? I think the other point maybe that the layering essentially works. I mean, it's a layering of rules, but it works by basically defining some kind of precedence on the types, saying that some types are handled by the rules before other types, essentially. So that's why you get this this relationship over the types. but as far as I understand, the precedence graph doesn't work at the type level, but at the instance level. Yeah, so I think in both cases you define some kind of ordering, but in one case it's on the elements, on the instances, and in the other case it's on the types.
Yeah, exactly. So in prior works regarding TGGs, so basically predecessor of my predecessor, there they defined the precedence relationship like you would say statically over your rules and try to analyze which rule applications should, like in general, precede others. But in general, so it's intrinsic a problem that you cannot do everything statically in that case. And so what we did, we moved that to the dynamic level, on the instance level, like you say, and we basically just analyze on, okay, what rule application do I apply? And then I just hang that into my precedence. I try to update that as I get these matches for my rules. And then I have the structure, and which directly reflects how each rule application that I have in my graph is connected and how it must precede others, etc.
Yeah. Okay. Yeah. So Paolo just confirmed what we suggested, I think, on the chat.
Yeah.
And
exactly. So it could happen that you can analyze the rules and you can see that whenever a certain, or whenever a marking that corresponds to a certain rule appears, necessarily there has to be another rule before that, because this other kind of rule creates structure that the other rule uses. Yeah, so this can happen, but we did not use this kind of information in our synchronization process. Maybe this could also be used in the one restriction that we have to get an efficient procedure is that we do not kind of reanalyze the precedence graph that that is not invalid. So if we have parts at the start of the precedence graph that are not invalid, they will never be touched. And obviously this restricts the kind of solutions we are able to compute, because in principle it can happen that by parsing that part in another way, we would be able to compute other solutions. And the condition of marking completeness for our completeness result excludes exactly situations like this. And this idea of taking into account such static information additionally, maybe this could be used to relax our restriction a little bit, to be able to decide which parts of the precedence graph to repass. But that's speculation from me. We do not use this information now, but I think it could be interesting.
Okay, so unless there are any other questions, I would maybe close the official part of the seminar now. Just see if there's anything else. Don't see any. So thank you very much again, Jens and Lars, for your presentation, and sort of, I think we all learned a little bit more today. So thanks for that. And I don't know, Nicholas, if you want to advertise the next talk.
Yes, so first of all, also many thanks from my side to you both, Jens and Lars. Thanks a lot, and also to everybody on YouTube interacted and here in the Zoom meeting. And we have the next talk scheduled for May 20, so that's in about a month, by Roy Overbeek, and it will be about PDPO plus writing, which is kind of mouthful, but it's like a nice new way of looking at that from a perspective of quasi-top-by. So that'll be more of a bit of a mathematical talk. And it might be that we have another talk in between, but for the moment, that's the next one scheduled. So if you maybe check the mailing list if you're interested. Yeah. Thanks.
Okay. So yeah, thanks for that. And yeah, thanks everyone again, and have a good weekend. Yeah.